Okay, so let's begin. So for our last talk of the day, we have Matthias Christandl, who is going to tell us about tensors versus entanglement.
But afterwards, we have the...
Oh, that's right. And afterwards, today is not done because we have a lot more fun during a problem session. And the problems are out there.
And on your computer.
That's right. And also GM has sent you the problem.
Carolyn, alums.
Okay. Okay, but the problems have been collected and they've been sent to all the participants, at least in the algebraic geometry program. So at 5:30, please come and people will present the solutions. Okay.
Okay. So thank you very much for the organizers, Joe, Peter, Bernd, and Ketan, for inviting me to give this talk at the boot camp, and in general for organizing such a wonderful program. So my research field is quantum information theory, and there are some connections between quantum information theory and algebraic geometry and representation theory, and so I would like to tell you about those. And so my title is try to be slightly catchy: Tensors versus entanglement. Entanglement being one of the key concepts in quantum information theory. I guess I have an hour 15. If you have any questions, just interrupt. There's no point in waiting till the end if anything is unclear. I also hope maybe Joe can remind me after sort of 35 minutes to make a break.
He's supposed to, but I will try.
Anyone. You can also do it. Okay, good. Well, so here's my outline. So I have three subjects. I first want to give you a very quick introduction to quantum information theory. Actually, let me do a poll. So who has a degree or studied mathematics?
What?
And who has a degree in computer science? And who's got a degree in physics? Okay, good. So I got a degree in physics, so but not in either mathematics or computer science. So quantum information theory is sort of an interdisciplinary field between physicists and mathematicians and computer scientists, but also these days engineers who help the physicists build some quantum devices in their lab. So then we got this I want to tell you specifically about entanglement. And the last one I call representation theory and the quantum marginal problem. This is sort of a problem which is kind of at the heart of the connection between quantum information theory and maybe the topic of this program here. I'll tell you later what that problem is. Actually, I wanted to rename it. I wanted to call this Kronecker coefficients. So it fits closer to what people think about it. Okay, so let's get started with quantum information theory. So in general, physicists are looking to describe the world, right? And until around 1900, there was sort of a classical description of the world, or maybe also you can think about Newton's description of the world in general. And then around 1900, sort of something changed, and people developed what is known as quantum theory. And quantum theory is the most successful theory actually we've ever had. It's the most precisely tested theory of atoms and other particles in the universe. And nowadays people are able to manipulate single atoms to very high precision. So the question arises, can you do sort of computation by manipulating quantum matter? And for that, in the last decades, sort of a very natural formalism has arisen, and I would like to tell you about this formalism. So that's a formalism. I'd say the formalism of quantum information theory. It's only slightly different from sort of the formalism of quantum theory. And I mean, really, it's the same, but it's sort of more in a computer science language. So to every physical system, so there's sort of some axioms, if you want. Maybe I say to a quantum physical system, whatever that is, you may think of an atom. You may think of an atom, you may think of a proton, you may think of a brain, you may think of everything is a quantum system. So to every quantum system, we associate a Hilbert space. And we denote the Hilbert space by H. Now, really, in our case, Hilbert space will just be a complex space, CD. And the difference between the Hilbert space and what we had before is that the Hilbert space is endowed with an inner product. So the thing has an inner product. That's important. And we're just going to assume this sort of very simple case where you have a finite dimensional complex space. So just, d-dimensional vectors. And then the state of the system is given by a vector in that space. And for historic reasons, I call this vector psi. So psi is sort of the wave function. And yes, and this psi is normalized. So the true norm of this psi square is 1, or if you want, if my inner product is like that, I have an inner product that's equal to 1. And then there was Dirac, who introduced some very handy notation that we use these days. It's the so-called Dirac notation. So if a vector is in the Hilbert space, we give it a line psi / wrangle. So that's sort of like code around it. So like a cat, we call this a cat. And you can of course make, because you have this inner product, you can make a dual vector. And the dual vector you denote by this. And the smart thing about that notation is that then this of course is if you take another one, right, this here is of course is a bracket. Right? So we call this guy here a cat. And this guy a bra. And together they form a bracket, right? Which is just your inner product. So that's our setup. This has one other advantage, this nice notation, and namely that if I want to if I take a vector that is, or a state that is normalized, namely has trace 1, and I look at the projector onto that vector, we just look at the orthogonal projector onto this vector. And normally people would maybe call it p psi, but I can now write this down like that. And because I want to be quicker than writing like that, I will just do this. Right? Okay. It's not an X in the middle, it's a wrangle angle. So, okay. Good. So now, You have the physical system, it's in that state, but when you want to observe some quantity of that system, you have to make some measurement on that system. And measurements are also described. There's a formalism for measurements. Actually, these guys here that I told you about, these are called pure states. We can come to that later, maybe. Then I want to describe measurements, but I'm actually, for simplicity, just describing what so-called projective measurements are. Shouldn't worry about it too much. Measurements are given by a set of projectors. Okay, so Pi is a set of projectors. The Pi are non-negative, right? And they're equal to their square, and they sum to the identity. So they're orthogonal. I haven't written this down. Right, delta ij maybe. Okay, so it's a set of orthogonal projectors. And now we have so this measurement is given by that. And now we have a rule for, right, so I have the system, I make the measurement, and I get some result on my detector, right? So I make a measurement and then some result flashes up. And the result will be this I. So if I perform this measurement described in this way on my system, then the probability to obtain outcome I will be given by graph psi pi ket psi. And after you've done this measurement and you received outcome I with that probability, okay, maybe you can easily verify that the sum of these probabilities, right, of course this here is a non-negative number, so it's fine. It's between 0 and 1, and they also sum up to 1 because these guys sum up to identity. Okay.
The sum of the squares is 1, or the sum is 1?
The sum is 1. So, all right, let's just do it. So if I sum the probability of this, that is just sum over I, psi, pi, psi. This is all linear.
Right. Yeah.
This is the identity. So this is 1. Okay. Because the inner product is 1. Thing is normalized.
So Pi is just, with its projection, you just pick an orthogonal basis, right? And then the...
Not necessarily a basis, actually. Doesn't have to be, it could be like incomplete. Like the identity operator itself would be a valid measurement.
Sorry, what does it mean great or incomplete?
But they sum to the identity.
They sum to the identity. How could it be incomplete?
Yeah, I don't understand.
Oh, sorry. Maybe
So,
I didn't
They can
understand
be
your
blocks,
question.
right? They don't need to be
They don't need to be.
complete.
They don't need to be complete basis.
but what do you mean then sum to the identity? The identity is the operator that's that's full dimensional, full rank.
No, but PIs aren't necessarily of rank 1, is I think what he's saying.
Yes.
Yes.
PIs could be rank 2.
Oh, I see. So I see. They need a projection, but they're not one-dimensional projections.
Right?
Okay.
Doesn't say that.
Okay.
Okay. Good. But it's yes, the most interesting case often is the case where they're one-dimensional. But here is okay. So anyway, so let's maybe I come to that later. It's sort of if you have you can also continue thinking about them being rank 1, but I would not like to do that.
Before you continue, what's the right-hand side of the equation 4 up
Oh,
from the
which
bottom?
one?
That one. Oh, down one. Down that one. Yeah, the right-hand side of that. What's that mean? Yeah. So we have psi of
Psi, pi, and psi.
Two vertical bars that you need to define.
It's like phi transpose pi phi in
All right,
in
so-
mathematical notation.
Okay, so mathematical notation. Well, okay.
Oh,
So
sorry, that's right.
No, it's fine.
okay, so no, it's important. We're going to do this now. So it's boot camp, right? So psi is a vector in this space there. I put a ket around if it's a column vector, right? With components psi 1, psi 2, up to psi d. And if I write like that, what I mean is psi1 complex conjugate, psi2 complex conjugate, psi d complex conjugate. Okay? That's it. Are you happy? Good. Okay, pose. So, right, you do a measurement, you get outcome I, but then you still got your system around that, your particle's still there. So you got it, right? So I have this particle, I make a measurement, I get some result, and I still have this particle, so I have to tell you what state the particle is in after I done the measurement. So the post-measurement state, given that I received outcome I, is pi psi divided by square root of the probability. Okay, of I. This is evidently some vector in the same Hilbert space that we started with. So that thing lives in H. And now you can also you can also convince yourself that the thing has again norm 1 because I divide by this probability. Right? Of course, if the outcome, of course I don't define this thing if the outcome has probability 0, right? So, okay, so that's actually why I insisted before on that I'm also happy with taking higher rank projectors, because then somehow not only, right, if this was rank 1, if this is rank 1, then
But this vector could easily be 0. Pi of psi could be 0.
sorry.
Pi of psi could be 0.
It could be 0, yes. So I said I only define this if this probability is non-zero. Yeah?
I see.
I mean, it's to have a well-defined quantity. Right? Otherwise, I don't need to find post-measurement state because the outcome didn't occur. I just look at the system and one of these I appears, and I get the I. If it comes out with 0 probability, I didn't get it in the first place. Okay. Right. So if this pi, right, is rank 1, then you could write it like that for some vector phi, and then pi applied on this is proportional to, well, it's actually, if I divide it by this probability, it's actually equal to phi. Okay. But that was sort of just good. So I have a note, following thing. Note that so this is all you can learn about your system, right? This is entire quantum mechanics for you here on the board. So all you can learn about the system is that you plot, right? You have a system in some state psi. You hammer on with this measurement, and then you discover what That's all you can learn about your system. This probability distribution. The probability of what this I is. So, therefore, in principle, the phase, right? You see it from the formula for the probability here. The phase in front of the psi is unobservable. Right? You see that that if I, when I multiply, if I'm going to multiply psi by e to the I tau times psi, because I have here the complex conjugate there, this e to the I tau just disappears. So the phase is unobservable. So in some sense, you may say that states of your systems are maybe just rays. You may now sort of, I just want to mention it, right? So states are in some sense equivalence classes under this. But it's good for us nevertheless not to think about them as rays in the Hilbert space, So to look at projective space, because we need this inner product the whole time. Okay?
So I'm
Step
just
aside.
slightly confused about this. Just sort of how to think about it. So you're given some state psi, and you basically all you get to observe are the outcomes pi of psi, or
Yeah, no, think about it this way. I'm not giving a state psi. I'm giving a physical system which is in a state psi. And then, for instance, the question could be, what is psi? Or, you know, so if you think about it, yes.
and
So think about a classical system, right? A classical system with maybe two states, a 0 and 1. And then, you know, you're getting this classical particle, this classical system, and you don't know if it's in 0 or 1. What do? Well, you make a measurement on that system, and you observe whether or not it's 0 or 1. And here it's the same thing. So you give this system, and you make some measurement on it, and then you observe what it is. Okay.
Excuse me. But if you make a measurement, the system may then no longer be in state psi anymore, is it?
That's right. The post-measurement state is given by this state. Right? The
And
system.
where do you get the PIs from? The physicist
Oh, the
design?
PIs are the system. Are described by your measurement apparatus. Right? You build some machine. Right? You build some machine, and this machine is described by the set PI.
Is it also possible that the measurement apparatus itself undergoes a change after you've deployed it? Or we discount that possibility?
We discount that possibility. I mean, of course, your apparatus could just burn or something, right? You did it and
So
suddenly
just
it's burned, but that's sort of like, you know,
I should
it's
think
like
of
there could be an
PI
earthquake. You know?
No, I'm saying I should think of the PIs as immutable mathematical quantities for the
Yes.
Okay.
Yes. Good. There's another rule. So, well, it's not all quantum mechanics, because often we haven't got just one particle, but several particles. Right. So, given systems with Hilbert spaces HA, HB, HC, etc. The joint system has Hilbert space H is equal to HA tensor, HB tensor, HC, etc. Okay. And of course, the states of the joint system are states in this tensor product Hilbert space. And of course, if I give myself orthonormal bases, say for HA indexed by I, yeah, this will be my standard notation for an orthonormal basis. We call it a computational basis for a Hilbert space. Ket and then just I, and then an A is a subscript if I talk about particle A. And if I talk about particle B, no, sorry. I should put this, right? Okay. And of course, punchline is states are tensors. And because we do quantum information theory and we got lots of particles, so if you think about computer science, right, you don't want to talk about one bit, you talk about strings of bits. We have this tensor product everywhere. If you think about a megabyte of, a megabit qubits or something, then quantum bits, then you have really many of them. So therefore we do some abbreviations here, and I'm just introducing them now. so we're not going to get confused later. Namely, the first thing, of course, we're going to drop the tensor product, right? It's obvious from the context. If I write this, I just drop the tensor product. What's in there? Okay. If I talk about three particles, this sort of writing this cat thing is also too long. So I will just do this. And then, of course, quite clear from the context, I'll drop this ABC here. Oh, wow. Okay, it's a boot camp. Time for some examples.
Just one more dumb question. Where does this restriction on PI being positive come from?
Well, I mean, probably this just implies it, right? What do you mean where it comes from?
Means why are we allowing only positive measurements?
Probability is positive.
Positive,
You can have
probability
interpretation.
positive, that would be one
Because
thing,
he
yeah.
wishes to interpret those as probability.
Yeah.
But I'm saying, is it because of physical consequence, or we could also take absolute value in there to make things positive?
Well, you're free, right? So you're free to decide any theory you like.
Yeah, I'm saying, but
You're free to decide any theory you like with like negative things, etc.
Sure.
The point is that sort of this thing that I wrote down, that sort of coincides with what you do when you like build an experiment in the lab. So if you go,
that's the thing I'm trying to understand.
Yes,
How
yes.
does the positivity coincide with what is built in the lab? But maybe
yes, because otherwise the probability. I think the answer was correct. Otherwise, these probabilities here wouldn't be positive.
So the straight non-inclusive means positive semi-definite, right?
Yeah.
Oh yes, I mean positive semi-definite, but
Yeah.
I'm not actually sure what is necessary. Okay. But so yes, so in contrast to sort of mathematics and physics, you're sort of constrained what you see in the lab and what you have there. So you have to sort of deal with that. Okay. Anyway, let's do some examples so you get a feel for what this is. And the example, of course, is going to be super easy. We're going to do C2. We call C2 a qubit. It's a quantum bit. Right? Why do we call this a qubit? So first of all, the 0 would be, maybe I put the 0 like this. The cat 0 is 1, 0, and the cat 1 is 0, 1. A general quantum state looks like alpha 0 plus beta 1. Of course, this I could write like alpha beta, where alpha absolute value squared plus beta absolute value squared is 1. You may write alpha as, I hope I got this right, cosine theta half, and beta as e to the I phi sine theta half, where theta goes from 0 to pi and phi 0 to 2 pi. Then you see that I could describe this. I'm not very good at drawing, so apologize for that. You could describe this as a sphere. So you can think of a qubit as a vector on the sphere. With one of the angles is theta and the other angle is phi. Okay. We call this a qubit. It is nice because up here, top vector, that would be like up and down, right? Are 0 and 1, and these correspond to the classical bit. So if I have 2 orthogonal states, 0 and 1, these would correspond to a classical bit 0 and 1. And a qubit just has more possibilities, right? That's all. A classical bit, 0, 1. Why do I call the 0, 1 a classical bit? Well, I could do a measurement. Well, here's a measurement where I have one of the operators, namely the P0, I take as the operator 0, and the P1, right, is identity minus that thing, so we're, I'm sorry for my European one. So if you add the two, you get identity. Right, so now you can compute the probability. What are the probabilities? So if you now compute the probability of obtaining 0, that is, well, right, just a reminder, that is that thing, and then you will be able to see that this is the same as alpha absolute value squared. And the probability of 1 is, of course, beta absolute value squared, and the two add up to 1. Now, if I have a 0, right, then the probability of getting 0 is just 1. And if I have a 1, probability of getting 1 is 1. So that's why it's sort of it's a classical bit. It's sort of clear, right? It's clear what it is.
Any reason why you would write theta half or not theta?
Then you get the sphere.
Yes.
You get a nice visualization. And the north pole is one classical point, and the south pole is the other classical point.
I want to have it from 0 to pi. Of course, you could go from 0 to pi half, and then it would be fine too. But
So sorry, you assume that alpha is real because phase is not observable, yes?
sorry.
You assume that alpha is real because phase is not observable.
Right. Yeah.
Right.
So then
Phase is not observable. I can adjust alpha to be real.
Sorry.
I think it was correct with the theta half. Was
You
it
want alpha
wrong?
to be anywhere
No,
between
I'm just
0
in
and
the
1.
figure I'm confused, but in the figure I thought it should be theta half with this angle.
But you know, you feel free to like relabel it and
Maybe I understand.
So you're going to go from 0 to 1.
I think the half has to do with the double cover of SU2 over SO3.
Okay.
But it's okay.
Okay.
Yeah.
That's some more
Um,
Okay.
deep explanation.
I see too, yeah.
Good, now I understand.
Okay, good. Right. So this is that thing. And of course your wave function, I mean, you know, right, it expands now in these 4 terms. So okay, sorry, this is a bit trivial, but I still want to do it.
Actually, the UOP ones are easier to read because you have so many bars in your notation.
Yeah, but you know, people here get confused. They think it's 7s the whole time. And then they start adding up. And then I'm talking about 77 the whole time.
Half the people here are Europeans.
Good. Anyway, so we go to next topic. Okay. Next topic was entanglement. Okay, entanglement. Okay, what is entanglement? Well, I said already before somehow that 0 and 1, these were the classical states. And likewise, 0, 0 and 0, 1 and 1, 0 and 1, 1 are sort of the classical states of 2 bits. Right? So everything that sort of doesn't look like 0, 0, 1, 0, etc. is in some sense quantum. But let's make this a little bit more formal, because of course I don't want to have the definition of quantum depend on my basis choice, my local basis choice. Therefore, we come with this sort of very mundane definition, and maybe sounds fancy, you thought entanglement was a fancy concept, but it's not. We're going to say a state psi in this Hilbert space, and is entangled if it is not, believe it or not, if it is not product. Okay, so if it is not product, and being product means that psi is
It is not of rank 1.
right. That's right, if it's not of tensor rank 1. One important thing is that actually, that this definition depends on the split of your Hilbert space into these tensor products. I don't know if one of the previous speakers emphasized that. I want to emphasize that. Also, all classical states, I mentioned that before, these kind of 0, 0, all these kind of bit strings, they are of course product states. Now, entangled states are quite important. So, definition looks very simple, but they're very important because in several areas. So first of all, they're important in most modern quantum experiments. So it's surprising, but you almost won't see any fancy experiment anymore as long as that doesn't involve in some way states that are entangled. So in physics, most exotic states that people construct now in the lab, they're entangled. You know, maybe ones that have been around for some time, like superconductivity states in topological materials, are right now very much at the forefront. Now in computer science, we have, in quantum computing, we have this algorithm for factoring numbers, Shor's algorithm for factoring numbers. And one can show that if the states appearing, if you can, that if there weren't entangled states, and if a quantum algorithm doesn't have entangled states, or only weakly entangled states, then actually you can simulate it by a classical computer. So that means that a quantum computer sort of fundamentally is based on the notion of using entangled states in some very, very sort of deep manner. Now, there's also the field of quantum cryptography that allows you to use entangled states in a communication paradigm where sort of one entangled particle is given to one person, typically called Alice, and the other is given to Bob, such that when they have access to these entangled states, then they're able to convert it into secret bits and communicate in perfect secrecy. So they actually sort of, these entangled states here, they circumvent somehow Shannon's theorem that you can't do this from 1940s. So you actually can do it. So you can communicate in perfect secrecy with the help of quantum mechanics. And maybe a last one, if you're interested in communication paradigms, for instance, function evaluation, several people want to evaluate a function faster than they can do this by classical communication, then also entanglement can help here and it can help speed up your problem.
Matthias, should I read mine?
Oh,
If
good.
this is appropriate.
How much? When does it finish? 4? No,
5.
At 5? Let's take a break.
Can I ask something? Where do you order entangled qubits? Like,
Where you order them?
yeah.
Why you go over to the physics
I mean,
department?
how do they make entangled qubits? Like, you know, they always say, okay, get 2 entangled qubits, give one to Alice, give one to
Yeah.
How do you
Well,
make-
one way of making them is there's sort of special crystals, known as PBO crystals. You can fire a photon on them, and then that photon splits into 2 photons whose polarization. So the polarization of a photon can be described by C2, this fashion. And you can these 2 photons that come out of that, they each have this T2, and they can be entangled in essentially in a state like that, 0, 0, plus 1, 1, which is a pretty far from product, as far as you get. I should put the normalization here. And because we're even lazier than that, we typically write.
So there's a procedure where every time you get
Now we're going
or
to subtleties.
micro.
No, this was not, this BBO crystal thing doesn't work every time, but you can nowadays produce them every time, yes. But then you have other functions. You know, we can talk about that break. But take your break. And get out. Get some chocolate.
Does it work?
Oh, thank you.
There's some senior problem.
Yeah, it's okay.
We can do that.
It's just that I typically see what I'm doing. Welcome back. Next question we are having is how entangled is a given quantum state? Now you know what entanglement is. How entangled is a given quantum state? And when is a quantum state more entangled than another one? These are the questions we want to address. And we're going to address them in this particular way. So first of all, we're going to, think about tensors in this sort of maybe more visual way by giving the 3 particles to 3 people, which we like to call Alice, Bob, and Charlie. Each has their associated Hilbert space, and there's some, they're somehow weirdly correlated. Okay. And the way we're going to do it is we're going to say that a state psi is more entangled than phi if psi can be transformed into phi by something called LOCC, by local operations and classical communication. Okay, so this is local operations and classical communication. So we think about it really literally. So Alice has some lab, maybe here in Berkeley, and then Bob's got a lab down in Stanford, and my friend Charlie Marcus in Copenhagen maybe has also a lab. And they have each a particle, and these particles are correlated, and they're given, their correlation is described by this quantum state psi. And now they want to transform psi into another state phi. And what they can do is they can do everything they can do in their lab. Particularly, they can do all these projective measurements. And they can classically communicate, meaning they can phone each other on a regular phone. Okay. This is a nice notion of transformation of a state because it doesn't generate entanglement. This notion someone doesn't generate entanglement in the sense that we had before. So if a state was not entangled, then applying LOCC doesn't entangle the particles. That's why we look at this class of operations. That's why it's natural. So what does local operations mean, actually? So local operations, or what is a sequence of local operations in classical communication? Okay. This is actually a sequence, like in a computer science protocol, it's a sequence of operations Alice and Bob can perform in their system. And the first, let's say without loss of generality, Alice starts. First thing Alice does, that's a local operation, Alice can actually attach another particle, of course, in a fixed quantum state, right? She can sort of bring another particle into the lab. Why not? That's certainly something that she can do. She can attach local Hilbert space H H maybe A tilde, in a state, in some fixed state. Right? That she certainly can do on her side. Then what she can also do is she can measure. Right? She can make a joint measurement on her on this joint Hilbert space that she has. Then she gets some outcome measurement result I, and she can communicate that measurement result I to Bob. Right? Alice tells Bob measurement result. Now it's Bob's turn. Right? Bob, attaches local space, right? HB tilde maybe. And then he makes a measurement. Bob measures. And note, Bob's measurement can now depend on the measurement result he got from Alice. Right? And then he measures, he gets a measurement result, he tells Charlie. Charlie attaches local Hilbert space and state in that Hilbert space. He makes a measurement, he gets a measurement result, he tells Alice. Alice makes, and the whole thing repeats. Okay?
So what about unitary transformations? Can you do that?
Yeah, it's somehow included here in this formalism.
I see.
Okay, I already included it because I allowed attaching this Hilbert space and making general measurements. I think it's okay.
Oh, because you can only measure one of the states. Alice
You're
can
right.
only measure one of the states, you're saying.
Alright, good, do it now. Let's take it offline there. It's not such a big change. Good point. Yeah, I could put them into my formalism from before with the measurements. Okay, what is important now is the following definition, right? So we say that this protocol LOCC managed to transform psi into phi if that worked with probability 1. Okay? So if
But it seems that phi is living somewhere else, or am I, because you're attaching different vector spaces?
yes, so I think in this sense of, you have a term for this, I always forget what it's called. What are these sort of equivalences?
But if you tell us what it was mathematically, then we might be able to help you out. I mean, what this procedure is.
Oh, I told you what it's mathematically. That just says here, right? So
you're allowed to start with psi, tensor.
Okay.
Tensor.
I'm allowed to start with psi, right? ABC. Then Alice comes in her first step. She attaches a 0 in this space. Okay. Then she will perform a measurement with some pi that live on AA tilde. And that will then transform her thing into some other state, psi maybe 1, that lives on AA tilde, B and C, right? Then, and she will get some outcome. And this state here will depend, this is going to be super complicated now. And this, she gets some outcome I. And that outcome I, right, she gets that state, she gets outcome I. There's some classical lamp flashing and says it's I. And then, and she gets that with a certain probability, right?
Yes.
Then she tells Bob I, right? Then it's Bob's turn. Bob has that state. He attaches the
But
0
how does
in
Bob have psi A tilde?
No, but the state of the whole system, the state of the whole system is described by psi AA tilde B C comma I.
I see.
So when I say Alice makes a measurement with operators AA tilde, what I mean is that if you think of the whole system the measurement operators for the whole system are of the form, should have said that maybe. They have this measurement here and their identity on the other systems. Okay? That are the measurement operators. And now it's Bob's turn, right? Bob takes that B tilde, a new Hilbert space, attaches this in 0, has that vector, or he doesn't have that vector, but their total system is described by that. He is now allowed to perform a measurement, and his measurement operators are allowed to act on B and B tilde. And because he got this result I from Alice, they're allowed to depend on I. Okay, then he does that. Then we get a new state on A tilde, B tilde. And now it depends on I and J. And now it's Charlie's turn, right? So now Bob communicates J to Charlie, etc., etc. Actually, may raise the I there. And so it continues. And then the question is at the end, so for me it's the ambient space is somehow not important. So I'm happy to, so if I'm talking about HA, if I'm talking about a vector in HA, I may include this into some bigger space. For instance, into this, I may view this as like living in, you have a name for this, we had it a few times during this workshop already. I may enlarge that space.
But you could assume that HA is given at the beginning, say, and it's everything that Alice can bring in, no? It could be some other tensor product, but that's one thing.
I want to have it separate, but maybe that's also a
The name
discussion.
was concise when you cannot if it's not contained in a small subspace. But it's not really
So I started with a vector in some Hilbert space, but I don't care if you make that Hilbert space bigger, right? We had these big discussions this morning about like finding like a smaller space on which the thing is supported. Now, frankly, physically it's irrelevant. Physically, I can always attach like some additional dimensions.
Because you're tensor producting with a classical state. That's the point. So you're not changing the rank of the tensor or anything.
Yes, I'm not changing the rank of a tensor.
That's, yeah. Okay.
So can I try to re-say what you just said?
Yes.
So it sounds like you're allowed to take your tensor and tensor with another vector, which is in a one-dimensional vector space, and you're allowed to perform some contractions, and then the border rank of the tensor does not go up during these operations.
Yes, I mean the tensors are locally equivalent.
But
by attaching something, they're locally
But you
equivalent.
could contract, you could measure, you could make a measurement.
Oh yeah, I can make a measurement. I can make a measurement.
Right? So
That's
the
right.
measurement could drop the border rank.
Oh yeah, sure.
Yeah, I mean, phi could
Also
be
the
pure.
tensoring.
Phi could be rank 1.
Yes, sure, absolutely. It can drop it. But you see, that's good observation. It can drop it. It can increase it. My procedure can't increase it. And you already seen that if I start with rank 1, tensor rank 1, then what I said before is my class of operations won't make it entangled. So it won't increase it to tensor rank 2 or higher. But it's true that if I start with something tensor rank 5, it won't increase it to 6 either.
I have a question. In Virginia's talk, she introduced this notion of restriction. I don't know.
Yes.
Is this LOCC the same? I mean,
Well, this is kind of...
Yes, it's similar actually. It's similar,
Exactly.
but what I'm requiring here, we're going to come to that. What we're requiring here is that we're doing that for all outcomes, right? With LOCC, I'm requiring that I get phi for all with probability 1 at the end.
So what's the advantage of tensoring with this 0 A tilde?
Because I defined my measurements to be just projections. There's no advantage in doing that. It's just that I can do it, and I'm doing physics, so I have to model this. So my Alice, Bob, and Charlie, they actually can do this. You can bring in another particle, they can do a measurement on the whole thing.
Well, why can't you just do a projection on HA to a subspace?
That's not generally enough. It will not allow you to. It will give you a lower set of things where you can transform to.
I see.
You can project to something diagonal inside of a tensor tilde. That's not available.
Yes, you can do more things with this. That's why.
Okay.
Good. Okay, so now what you can then, of course, study, right? You can try to understand. So one of the goals in quantum information theory is maybe to try to understand this relation here. Which pairs can be transformed into each other, or when can you transform psi into phi? And of course, a natural thing to look at is what we call entanglement monotones. This is just monotone functions. So I'm going to say E is an LOCC entanglement monotone. If E of psi bigger than E of phi, for all psi LOCC.
So yeah, so potentially this is even relation on things in different spaces. That's what I was asking. So
Yes.
psi could live somewhere, and then phi could live somewhere
Yes,
else.
but I'm going to embed them in like a big enough space so they both live there.
Okay.
Okay, I'm always going to, I can always re-embed into bigger spaces. It won't change anything.
So what
From a
is,
physical perspective, it won't change anything.
what is E? It's a function?
Oh, E is a function. It's a function. E is a function into, it's a
No, that's fine, as long as you say a function.
real valued function. And yes, I mean, I can of course say I'm only comparing things on the same dimensional Hilbert space, and but often I will actually look at functions that are defined on all Hilbert spaces.
Can you give an example of two tensors that one is more entangling than the other?
Yeah, I'm gonna. You see, I'm coming with that.
Sorry, I still may have one question. So, are the observations on A tensor A tilde somehow bigger than just those induced from A?
Yes.
Yeah.
And that's the game, okay.
Yeah, that's the point. That's why you can do it. I could have. Okay, alternatively, I'm just saying it, and then I'm going to continue. Alternatively, I could have defined somehow my setup a little bit differently in the beginning with my axioms. I chose this way because I think it's simpler. Okay, here's the example. Let's look at our simplest example. And I want to get to something else too, but we'll see. As I have to bite into discussion time. Okay, good. So we're going to take this, we'll call it bipartite Hilbert space. And let me first give you some examples of. So one thing I can do is this is a matrix, of course, I can do singular value decomposition, and I can get like some singular values SI here, and I get some new bases which I denote by EI and FI, and then this thing is diagonal. Right? Okay. And this goes from 1 to the rank. So very natural entanglement measures, and you can verify that maybe as an exercise if you still have time after doing all the other exercises. That the rank of psi, or this R here, you can verify actually this is an entanglement monotone. Yeah, but that's an exercise. We actually, you had already discussed it in some sense before. But there are other ones that are quite interesting. So for instance, if you take these SIs and you take their absolute value squared and you call them now RI, not to be confused with the rank. Maybe I should just call it rank psi. Okay, that uses a set of numbers. You can convince yourself they sum to 1 and they're non-negative. Well, they sum to 1. So they are a probability distribution. And of a probability distribution, I can, for instance, take the Shannon entropy. So if I take the Shannon entropy of these R's, in which is just defined minus RI log RI, this is also an entanglement monotone. And then there is some invariance. This is also interesting. So if you restrict now the dimension to be 2 by 2 only, then a entanglement monotone would be the following function, which I'm sure all our invariant run this record. Let me simplify. And okay.
Sorry, because it seems that you distinguish the bases. So is it like, so for rank we know that it doesn't depend on the basis, but for this second thing that you define.
This here.
Yes.
Yes, I defined exactly. So for each matrix here, there exist two bases, one for this one and one for that one,
Yes.
such that I can write in this form.
Yes.
Absolutely right. EI and FI depend on psi. I obtain them by singular value decomposition. Make a singular value decomposition of this thing, you obtain a unitary, your diagonal, and another unitary, and one of the unitaries will transform this I into the EI, and the other one will transform this into the FJ. Okay, now let me...
And what are these epsilons?
epsilon, no epsilon.
Yeah, I think signs of
Oh, these are signs.
Signs of the... What are the epsilons?
No, it's the...
Well, what are those symbols on the lower right-hand corner of the board?
I think they're just quantical delta image.
Kronecker delta. Okay, so then they should be delta I1J1, right?
Maybe. Think about it. Probably is deltas. Okay, let me give you a theorem. Nice theorem, and then I want to do one more thing, and then we're done. So this is a theorem by Nielsen. Very cool theorem. The theorem tells you that right, I define these singular values, right, for this guy has singular values. I call them R of psi.
So
and this
when
guy
the-
has singular values. I
when
call
the-
them R of phi.
Case of tensor product of two Hilbert spaces now.
Yes.
Okay.
Sorry. Then, if this guy majorizes that guy, then this transformation is possible, if no negative.
So this means the partial sums are strictly bigger.
Right.
Yeah.
The partial sums of psi are strictly bigger than that. For instance, this relation here immediately implies that this entropy statement here.
So this is the dominance order of the singular values, or what is, just to, sorry.
No, we are not talking singular values. Singular value is absolute value squared.
What is R, sorry, now this.
RIs, the RIs are the singular value square.
Square of the singular value.
Yes.
Okay, sorry.
So these here are the singular values.
Yeah.
Then take the absolute value square and call them RI.
Okay.
But singular value is always non-negative, so you don't need absolute values. It confuses
Fine,
the
drop it.
definition.
It's okay.
And they are sorted here when writing that partial order.
Yes.
Doesn't matter, summing them all.
Yes.
So means
Yeah, sorry.
that's bunch of n inequalities.
You know, just as they're
Then
just as you know, people who take them positive, they're also orderly. That's right. That's what.
So it's a weak majorization, as it's also known in math, as I guess.
Should I write it down? What it means?
No, yeah, will be good.
I think it just means that Ri of phi,
Oh, I see what you mean now.
I from 1 to k is, hold on, bigger than, let me do it like this. Is smaller than for all k, and now to be careful, and I want to start with the biggest one, right? So Ri is bigger than Ri plus 1. Right. Here we go. That's a nice theorem. It's not so easy to prove, actually. It takes, you know, it would take another hour. Okay, but what I want to say is that this is a spectacular theorem because nothing similar is known for 3 tensor factors. Okay, for 3 qubits, C2 tensor, C2 tensor, C2, you can still do something, but there it stops. That's why it's amazing. Otherwise, it wouldn't be so amazing.
What would be a canonical reference to see a proof of that?
Oh, there's a book.
Can you
There's by Nielsen and Chuang. If you just type in Nielsen and Chuang into Google, I'm sure there's one book that comes up.
You know, maybe I'm completely wrong, but it reminds me of a theorem where you look at degeneration of matrices under pairs, matrices under conjugation, Jordan normal form, and you look what are these degeneration orders, and they also get such a complete characterization where these dominance order appear, etc. So it's in Kraft's book, I think, the first pages. I wonder whether there's the relation between
Maybe.
these things. Looks very similar to me. So
Let's do it in the break.
okay, let's talk about it.
So, okay, what I want to tell you is that with probability 1, right, the statement here from before, you know, it's very hard. Nielsen did it for the case of 2 tensor factors, 3 tensor factors, out of the question. Okay? So we're going to modify our question, right? So we're gonna do this here. We're gonna do this transformation just as we did it before, but we're happy to say that we transform psi into phi if, okay, we're gonna write SLOCC instead of LOCC if the conversion that I wrote down before happens with probability bigger than 1, okay, bigger than 0. So, all right, so you do this whole protocol, and every time you get all these, you know, Alice gets measurement outcomes and Bob gets measurement outcomes, and they all come with like some probabilities. If at the end of the day there is just the probability of having phi is non-zero rather than 1, then we're going to say psi has successfully transformed into phi by SLOCC, where this S stands for stochastic. Okay? Okay, that thing is much easier because of the following very nice lemma. This is due to Dürr, Vidal, and Sirac. Namely, it says that psi SLOCC phi, if and only if there exists matrices, you know, the matrices on HA, B are the matrices on HB, and C are the matrices on HC, such that A tensor B tensor C applied on phi, psi is phi. Okay. So that's the connection between quantum information theory and algebraic geometry. Right. So I'm looking at tensors. My natural equivalence relation is the same as your natural equivalence relation.
Restriction, what we call.
You would call this like a restriction, that's right.
So restriction
Or
is
if I'm,
small.
yeah, exactly. Or if I'm sort of, you know, I could take the corollary and say, when can I transform psi into phi n backwards? And then I just get GL here, right? And I have like, or SL, whatever, because now I actually don't care about the length of the vector anymore because things only have to happen with probability positive. So I'm not actually caring about what the norm of these things is anymore.
Does it work
Okay.
for more factors than 3? Or
That works in general, yes. So that's a very nice lemma, and I will bite into discussion time because you are asking the whole time.
So I'm confused because I thought Alice could apply any unitary transformation to her qubit.
Right.
So
Oh, this is a lemma. You have to look up the paper. You know, that's the paper. Psi transforms into, you know, I asked the question, when can I transform psi into phi with SLOCC? And this is the answer. If and only if there exists three matrices such that this is equal to that.
So the issue where you need SLOCC is...
Oh, these are matrices, right? Arbitrary
Not
matrices,
necessarily
not unitaries only.
So that's
Matrices,
the-
it's really arbitrary matrices. And if you do it backwards, right, then if you want to have both directions, right, if you want to say when can I transform this with SLOCC and when can I do it backwards, then of course, you know, the MN just changes into GL, right? And then you have general linear group, and it's acting in this triple factor fashion.
Is there an easy example where the transformation is LOCC but not SLOCC? LOCC but not SLOCC? Is that more restricted?
No, I mean, SLOCC is, you can do everything.
Oh,
Right, if I can do something with positive probability, I can also,
Okay.
I mean, if I can do something with probability 1 is in particular a positive number.
Okay, and is there an example that is, so the
Yeah.
question other way around?
Essentially everything else.
Oh, okay.
I mean, with high probability, you'll, you know, think of a large enough space and do something, and then it will not be doable by LOCC.
Oh, okay.
But I guess so this theorem should already tell you what happens for matrices because, well, one of them was already characterized as LOCC, which should be...
Yeah, for two things, that's right. For two things we have this nice theorem, but for three and more, and I mean, that's sort of why we are here, with tensors, etc. For three and more, that's our interest. That's why I wanted to tell you that, you know.
So you can see for two factors, if you start with a full rank matrix, you can transform it to anything.
Right.
But by SLOCC, but not by LOCC.
Absolutely. That was a good point. Should have said that. Good. So let us. This paradigm is so nice that I want to do your, you know, your good old friends. I want to tell you that we like them too. So, what are your good old friends? Well, your good old friends are is this guy, for instance, right? I normalize it. This guy is Peter would call the unit tensor. We've seen it a couple of times today. We call it the Greenberger-Horn-Zeilinger state. So if you really, okay,
It's much cooler.
it's much cooler. It's a Greenberger-Horn-Zeilinger state. It exhibits some very fancy notion of non-locality, and you know, anyway. What we
If I
got?
had known before, 20 years ago.
Yeah, but it comes better. It comes better. Now, let's see. Okay, let's see if let's see how far. And maybe Peter knows. I'm excluding the people who already know the answer to the following question. You're not allowed to shout the answer. Okay, but the people who see this for the first time are welcome. So I'm giving you this state. I give Alice 2 qubits. Okay, Alice has a qubit here. So a 2-dimensional space, tensor a 2-dimensional space, Charlie has a 2-dimensional space, tensor 2-dimensional space, Bob has 2-dimensional space. I'm gonna write down, you know, they have 0, 0 plus 1, 1, they have here 0, 0 plus 1, 1, and here there's also state 0, 0 plus 1, 1. Okay, do you know this guy? Ever see? No. No idea? Okay. It's a 2x2 matrix multiplication tensor. Okay, I love this one. So this is actually the 2x2, this is your exercise, right? That's your homework. Show that this guy here is a 2x2 matrix multiplication tensor. So one of the very fundamental, this is very easy to produce in the lab, right? You just as I said before, you just take this crystal, you fire a photon on it, you get 2 photons out, and you know, Alice does it, right? Alice takes one of these photons, sends one to Bob, and keeps one herself. Then she's going to do another pair of particles and sends one here, and Charlie's going to do this here. So they have this quantum state, which is actually the matrix multiplication tensor. This is more difficult to produce. So we may ask natural questions, namely, you know, can I transform? Let me denote this guy by that, and this guy by that.
Sorry, so they each have 2 qubits?
Yes, they each have 2 qubits, so it's a C4.
So it's C4 tensor, C4 tensor, C4.
Okay, so I can, for instance, ask, can I transform the GHZ state into the matrix multiplication tensor? With SLOCC, natural question to ask.
But the GHZ is in C2 tensor, C2 tensor, C2, right?
That's right, but I could, for instance, enlarge the space. Or I could produce it many times, right? So for instance, I can produce it n times, or m times, right? And I can ask you, I'd like to have n of these, actually we call this state here, you'll not believe it, this is the famous Einstein-Podolsky-Rosen pair.
Better.
Okay, so this is the so-called EPR pair, defined by, or consider this guy, one guy, right? So you can ask this very natural question: how many GHZ states do I need to get like this triple Einstein-Podolsky-Rosen pair thing? And then I can look at the limit as m divided by n maybe for large n, right? Do you know what that is?
It's either an asymptotic rank or an asymptotic
What is it?
pole. It's omega. So
It's omega. So, right. So the conversion rate of so if you start with this state here, this is sort of a rank 2 state, right? Tensor rank 2 state. You can produce, all tensor rank 2 states here by SLOCC. So if I give you like a whole array of them, like if I give you this state tensor n, right? Then this thing is the unit tensor of rank 2 to the n. With rank 2 to the n, I can produce any quantum state, or any tensor with SLOCC with rank 2 to the n. In particular, if my matrix multiplication tensor, if n copies, 2 to the m, if n copies of the matrix multiplication tensor have rank 2 to the m, then I can produce them from here by LOCC. Right? That's why I get the matrix multiplication exponent. Good, maybe enough of
So
that.
delta is the GHZ state.
Yeah, delta was the GHZ state, so I tried to explain it. I just wanted to have some more fancy notation. These like long written out tensors, like I can't do it. Good. So, well, I think that's it. Because what else I want to tell you? I want to tell you about the quantity coefficient. Well, we can't do this now. I think it's too far in. So, thanks a lot.
All right, so there's still more time left for questions. So other questions?
I have a question. Maybe this is a ridiculous question, but Nielsen's theorem for more than 3 factors, if there's such a theorem, is there any chance that it's just that the eigenvectors of the tensor of a given format are dominated by the eigenvectors of the tensor of the other, from phi and psi? Take the eigenvector tuple for psi and eigenvector tuple for phi, and
I don't know what the eigenvector tuple is. So this is a vector itself.
well, it's an element of a tensor space, and so you can compute its eigenvectors.
What are its eigenvectors? What are the eigenvectors of the tensor?
It's complicated. That's all you have.
No,
to
you
Then I
have
don't
singular
know.
values, just for
Or
2
you can
factors.
singular value, so
It's not
you can define it
eigenvectors.
as some critical points of the function on the product of spheres, something like that.
I don't know. Maybe we talk about it later. I really don't know. So for the 3-qubit case, someone worked it out in their, they had some invariants that they defined and expressed the equivalence relation in terms of invariance, but it got very messy.
So maybe just to test my understanding, in this theorem by Nielsen, if you replace this LOCC reduction by the SLOCC stochastic,
Yes.
then we would get just the usual tensor rank? Or what is then?
Yes, then it's just rank.
Just usual
Yes, that's
tensor rank.
what Joe already
Okay.
said before. Then it's just rank, right? So the rank of one just has to be bigger than the rank of the other. So you see it gets significantly more complicated
Right.
when you go from, you know, suddenly you get like the magnitudes of these things here. And so it gets significantly more complicated.
Any more questions?
Maybe one comment to Peter is of course that you know, a monotone for this SLOCC thing here. Before I defined LOCC monotones, but I can define SLOCC monotones by functions that go down on the SLOCC. There, of course, I have things like tensor rank, border rank, you know, and this amortized or regularized or whatever you call it, tensor rank. You know, like omega, for instance, is also, I mean, yeah, things like that. So you have these other kind of functions. There are also some invariants which are monotones. Yes. So in general, right? So the distinguishing, you know, say if I want to look at all the things that are equivalent, so that I can transform back and forth, then I just get into SL orbit classification. So I just want to classify, right? That's the same problem. It's just classifying SL cross SL orbits, and that, you know, all that sort of ties into this program.
Okay, so let's not forget the homework session, which will happen in 15 minutes.
Paradox.